So here we have reproduced the dipole moment as a function of time. I just split up the exponentials. Right? So what we need to do next is to compute the time correlation function of the dipole moment operator, or dipole moment, sorry, this is classical. It's hard to not say it. But. All right, well that's easy because we really just need to multiply by mu naught again and then do the ensemble average. All right, so let me show you how we can do that. Well, we can just plug it in. So we're going to get mu naught squared doesn't really need the absolute value. Whatever. I'll just leave it like that. It doesn't make any difference anyway. And then we have everything the same. We do the average of that, of course. All right, and now, of course, we have to make a bit of an approximation. So the approximation that we're going to make is that we can essentially split this up, okay? And instead of having a correlation between this exponential and this exponential, we're going to say that they are uncorrelated. But the ensemble average of the frequency fluctuation is not dependent on the instantaneous frequency. If they're independent, then of course what we can do is we can write down the average of mu naught squared is just the average of mu squared, the dipole moment squared. And then the idea here is that we have the expectation value, or the ensemble average of this exponential, which just means that we're going to compute the same, it's the same thing. There's only one average anyway, so we just pull it out. All right, and then we're going to have another function that we'll call f of t for now, which is all the rest of it. So let me write down f of t. So f of t is just this ensemble average of the exponential. All right, so this is the thing that we have to struggle with, this piece here. This is easy, and this is, a number, as it's not a number, but it's a function of time that's very simple once we know what the average frequency is. So this is not so easy, and so there's two routes you can take, of course. You can simply say, I will just always do numerical simulations, in which case it doesn't matter. But if you want to try to analyze it by some kind of analytical formula, then we're going to need to do a tiny bit more work to express this in a form that we can tolerate. Okay, so I'm going to show you, this is in some sense a little bit of a mathematical aside, and then I have a file that I'll put on Canvas that does all the tedious derivation intermediate steps. Right? There's too many to do here. But let me get you thinking about this. What we want to do is we want to take not this function, but something similar to it. Just e to the I kx. So we know that we can write this as a series that we sum. In the usual way that we can express an exponential. So if we wanted to calculate the average of this, then we can do that. It's just going to be the average of each of these terms, right? The k is a number, and so it's the x that's going to be the important thing. So this is going to be equal to n equals 0. Right? Because if I write this out as a sum and I do the ensemble average, just like we talked about many times, the ensemble average is like linear. It distributes into all the terms of the sum. So that's here. The n and the k and the I don't average. They're just constant. So this is the only piece here that needs to be averaged. Okay, and so this is a way of getting you to see that you can take a function that's like this and convert it to a sum of averages of lower, of, like in this particular case, these polynomial. Okay, well, this is certainly the correct way to write an expansion of this, but it turns out there's another way that you can write an expansion of the this average, and it looks like this. Instead of starting at 0, you start at 1, and then, so some of it will look the same. Then you have these functions, these Cn functions. And one of them, C1, is the average of x. C2 is the variance. C3 is something called the skewness. And there's more of these terms. And these terms are called cumulants. And they come from probability theory or statistics. It's just another way of representing a distribution. You probably know that you can represent a distribution by its so-called central moments, like the average of x, the average of x squared, the average of x cubed. It's almost like it's like a Taylor series for a probability distribution. Well, this is just a different way of doing it. And there's a reason why we do it. And the reason is because if the variable that you have that's inside those brackets is actually distributed Gaussian, so if x is really a Gaussian distribution, then only C1 and C2 are non-zero. That makes it very simplified. All the other ones, amazingly enough, cancel out. Okay, so that's the setup. Now the step that I'm not going to prove, but I have a write-up for it, is to show you that you can use this for, instead of just these averages like this, you can use them for the correlation function, or like the exponential operator that we have here. All right, so we can write this f of t using cumulants in this way. So just looking at this, we know what the average of the frequency fluctuation is, right? That's 0, because we presume that it averages out to 0. So this first term is automatically 0. Now this is, you'll see why people like to use this so much, because it simplifies things dramatically. All right, then we're going to get 2 integrals. This looks a little bit like when you do the substitution, but it won't be exactly the same. Mostly in this integral here, you see that it goes to t and not tau 2. And then in STEM, the next bit is here. And then there are all the other terms, for sure, if you have a generic distribution. But if we are presuming that the frequency fluctuation obeys a Gaussian statistics, then only the second order term and the first order term are non-zero, so all the rest are 0. And what do we know about the first term? The first term is 0. So that leaves us with just this one term here. All right, so that means we can approximate this if Gaussian. I'll put a little G symbol here. So we have these 2 integrals. And you'll see in a minute, we're going to convert the 2 integrals into 1 because the we only care about the time interval. Oops, what did I do wrong? This. All right, so this is our f function. Sometimes it's called the dephasing function. So we're going to make a change of the variables. Would I miss I missed something, right? Yeah, d tau 1. We're going to make a change of the variables. So we're going to call tau will be equal to tau 2 minus tau 1. Right? This is a stationary equilibrium process. It doesn't really matter that there's 2 times. We only care about the time difference between the two, between these two. And we could have set one of these times to be 0, for example, which is of course what we'll do. So we set this equal, we set tau equal to tau 2 minus tau 1. All right, and then we can just like substitute it back in, which when we do this, I'll keep it in green so we remember that we've done the situation, this substitution. So when we make the variable change, first of all, we know that this I squared becomes a minus sign. And this 2 factorial is just 2. We're dividing this by 2. Right? So the idea is that we have the integral twice, so we're just going to have one integral, which is the same function integrated twice, so that the 1/2 will go away. So we'll end up with one integral from 0 to t, our time difference, and then we have to include this changing of variables, right? We include that. And then we have delta omega of 0, delta omega tau, which is what we want. Whenever you see something like this, a correlation function with 2 different time values, usually the strategy to make progress is to switch it so that you only have the interval. We've done that a few times. All right, so we're almost there. This is pretty amazing. Notice that we have discovered or revisited or refound this very important object, the time correlation function. So this is, we sometimes call this the frequency fluctuation correlation function. The reason why this is important is because it is used to calculate the absorption spectrum. So in principle, you could think, oh, that's cool. If I measure the absorption spectrum, then I can figure this out. The problem is there's no way to go back, right? There's no way to go from the absorption spectrum to this, but you do need this to go forward. Right? That's an unfortunate process because we lose some information when we actually calculate the absorption spectrum. All right, so what we're going to do is we're going to define this thing here, and we're going to call it C. You could call it C delta omega if you want, of t, or just C. Save a little bit of time. All right, and so what we're going to do with this correlation function is we're going to assume that it has like a variance, like we discussed before, and it has an exponential decay. All right, so we say, let's put it up here. We say C of t, it will be equal to delta squared e to the minus t over tau c. Tau c is the correlation time. All right, so we simply plug it into there. I'm still in the green. I'll use the pink so that we know that we're making this substitution. All right, so we have now f of t again. This thing, which is almost the correlation function that we Fourier transformed. The rest of these numbers, this is not interesting. This is going to give us our center frequency, right? So where to look in your spectrometer. Also not that interesting. You should know that. And then how strong is the band? That's also interesting, but that's not really what we're trying to understand in this class. Okay, so here is the piece that we really want, which is the f of t. All right, and the way we can write this down is like this. So we have minus 0 to t d tau, t minus tau, delta squared, and then I have e to the minus t over tau c. Okay, so what we're going to do, I would say that the key piece that thing that we want to analyze is here. We needed to do all of the work of making the cumulant expansion, substituting it in, and picking a form for our time correlation function, which was to say that it has a Gaussian statistics but an exponential time dependence. Now, if you're remembering, the Gauss-Markov process that we discussed in the discussion on Monday has those properties. So you can use a Gauss-Markov process to get yourself data that would have this property. Okay, so we'll clean it and we'll analyze this equation here. Okay, so we're going to take this formula and we're going to do the integral first. All right, so let's do the integral. Plus t over tau c minus 1. There's nothing special here. This is just the math. Okay, so now what we're going to do is we're going to analyze basically this equation in two limits. One, where the correlation time is long compared to our sort of t, the measurement time that we're considering. And the other case is when t is short compared to that. And we're going to see what happens when those two cases occur. But the important thing is they come from the same starting point. The thing in the box is commonly called g of t, which is the line-shaped function. All right, so basically we're going to be looking at g of t for a couple different sort of limits. So the first limit that we're going to consider is tau c is greater than t, which is to say that we're looking, here's our thing decaying, we're looking at a time that is much shorter than the time correlation function, so decay, characteristic time. Let's say it's there. So we're considering the region in time here. All right, so let's take a look at that. What do we have to do? We basically just look at this and we see the only thing where we can do any work is on this exponential. The exponential can be written as a series and then truncated. It turns out the right one to do is to go to the second order, right? So we're going to do that. So we're going to write this as 1 minus t over tau c plus t squared over 2 tau c squared. And that's how we stop it. And we plug that in. So this is going to be, we'll do the g of t. So g of t is tau squared tc squared. That's the stuff out front. Remember, the minus sign is not part of the g. It's part of it'll be in the exponential at the end. Okay, and then we plug in our expansion for the exponential. And that will be 1 minus t over tau c plus t squared over 2 tau c squared plus t over tau c minus 1. Okay, so we notice that there's some cancellation and some terms that survive. So one thing that cancels, of course, are the 1s. The t over tau c cancels at that t over tau c, and we're just left with this term here. The tau c on the denominator, tau c squared, cancels this tau c here, and the whole thing ends up being delta squared times t squared divided by 2. Okay, so let's look at what the f function then becomes. F of t will be equal to e to the minus gt, so minus delta squared t squared over 2. So what is that? What's that function? This function is a Gaussian, right? And remember, what are we trying to do here? We're trying to calculate this time correlation function. which is equal to the modulus squared, or the magnitude of the dipole moment squared, the frequency, so the oscillatory part, and then this f function. Okay, so what that means is that when we compute this and do the Fourier transform to get the absorption spectrum, we're going to have a Gaussian, because the Fourier transform of a Gaussian is also a Gaussian. All right, so this gives us a Gaussian line shape when we assume the time correlation function is much longer than the time that we're considering. All right, so this is a classic example of what people call inhomogeneous broadening. Now, why is it called that? So historically, you could think of truly inhomogeneous distribution. What is it? What are some examples? You should think about limiting cases to make it really obvious. So one of the super obvious way to have an inhomogeneous distribution would be to have literally different molecules in your sample. You know, you're not maybe the best synthetic chemist, and so you make a distribution of these conjugated molecules, and they're all going to have different frequencies. Never will this molecule switch and become this molecule. So the frequency fluctuations will be extremely slow, because you'll not be able to ever switch between these two. That's about as slow as you get, infinitely long. Now, that's a really extreme case. Let's give you an example from the physics community. So if I have a collection of gas molecules at some finite temperature, of course they're moving all over the place. Some will be moving one way, some will be moving a different way. And what we know is if I have a laser beam that's going in, it has a wavelength. Right? So the molecules that are moving towards the laser are going to see the peaks of the field coming more frequently than the molecules going in the other way. So the laser will seem blue shifted to a molecule going this way, to higher frequency, and red shifted to one going away. So this is called the Doppler effect. Right? And the Doppler effect is one of the limiting things that determines the line widths of absorption for gas phase molecules. It's the same thing as the ambulance or any other thing where you can hear the field. And the idea is that these molecules could hit the wall and come back, right? But they're probably not going to do that while they're still coherent. So this is a kind of static inhomogeneity, just like the Doppler effect in the, sorry, not the Doppler effect, but having the different molecules synthesized. Now you could argue if you have them at very high density, they could bump into each other, and then they would change their frequency or their direction. That could happen too. But for low density, then that's never going to happen during the time scale of your measurement. And by that, of course, we mean the coherence. Okay, so that's two examples of inhomogeneous broadening. Let me give you one that's much more relevant for chemistry. Classic case. If you have the OH stretch in water, for example, or in alcohol, it can be hydrogen bonded to another water molecule, and in general, it will be. Each water molecule can make two hydrogen bonds where it's donating, which is this case here, donating to that one, and two where it's accepting. That's one of them, and then if there was another hydrogen over here, it would be accepting. Now, one thing that we know is that the frequency of the OH stretch, which becomes localized in hydrogen bonding because this effect is so strong, the difference between symmetric and anti-symmetric, it goes out the window and you end up with just a single OH stretch and another one over here. This frequency is very strongly dependent on the distance between the two oxygen atoms. It's almost entirely, it's not linear, but it's pretty close. The function looks something like this. Which is to say that as you make the distance between, as you find, because you're not making anything, as you find the two oxygens, farther away, the OH stretch frequency will be higher. As far away as it can be would be like the gas phase, and that's the highest. And then it gets redder and redder and redder as the hydrogen bonds get shorter or stronger. So this is the OO distance, and this is the frequency of the OH stretch. Now, does a water molecule stay like this forever? No, of course not. In the next instant of time, very soon after, it'll find a different hydrogen bond distance. So its frequency will shift. Right? So if we can study, for example, the OH stretch frequency, it's going to tell us about what it sees around it. It's a spectator of the nearby solvation environment. Turns out there's a trick you can do that's even better than this. You can replace this hydrogen with deuterium. Just by adding a little bit of D2O to your water, they'll be exchanged because of the autoionization of water, and eventually you'll have a mixture of HOD in water. You'll have no deuterium molecules, no D2O anymore. It'll all get converted to HOD. Now you can look at the OD stretch and see all the water molecules around you. If you wanted to know what D2O was like, you could start out with D2O and add a little bit of H2O, and then you would dilute that. And that gives you a local vibrational probe of the environment without having to worry so much about the fact that these vibrations, if it was OH, for example, are nearly resonant with this one because it's the same transition, basically. That causes all kinds of problems for the spectroscopy of pure water or pure D2O. But if you isotope substitute, it gets much simpler. And then looking at the OD stretch tells you about the dynamics of the water. Primarily, of course, hydrogen bonding changes, fluctuations, and reorientations. All right, so these are classic examples of inhomogeneous broadening. If you look at the OH stretch spectrum of water, it's very close to being Gaussian. There's a reason why it's not exactly Gaussian, and that's because the Condon approximation doesn't really quite work. You can't just factor out the dipole moment and the frequency. These are not indistinguishable. The point is that for the frequency of different amounts, so as you have a different frequency, it means that you have different hydrogen bonding. The actual transition dipole moment, which is this, changes. Like some transitions are just stronger than others. So because of that, it reweights the way the spectrum looks, and it doesn't look perfectly Gaussian. Fortunately, we can, I would say, completely understand this effect, and it's beautiful. I love it. It's very powerful. And the 2DIR community has done a lot to basically, in my opinion, largely solve this problem. Okay, so that's an example of inhomogeneous broadening. I should say that we want to work out what the absorption line shape is, so let's do it just to clean it up. All right, so the absorption line shape is sometimes denoted with a sigma. And what you're going to do is compute the modulus squared of this dipole moment. Remember, this is the classical calculation. If we were doing this purely quantum mechanically, this would be the transition dipole moment. dt e to the I omega t. We're doing the Fourier transform of the dipole moment correlation function. And then we have e to the minus I, the average frequency, t up, and then minus g of t. Right, and then we know what g of t is because we just plugged it in. Right, and g of t is the positive one, that's why it's minus here. Okay, so we're going to put that in. This piece here becomes e to the minus I omega t minus delta squared t squared over 2, which you can literally solve. So this is the square root of pi mu squared, the constant that tells us about the strength, e to the minus omega minus the average squared divided by 2 delta squared. Right? And so as we suspected, but we knew it's a Gaussian, it's shifted because of the way that we have this up here, so that the center of the peak, of course, is centered at the average frequency, and then it has a width, given by like delta squared.